Today, we're tackling a question every coder has asked at some point. What really happens when you compile your code? Specifically, we're focusing on C++, that powerhouse language behind everything from AAA video games to operating systems and even high-frequency trading systems. If you've ever typed a simple Hello World program in a .cpp file and hit compile in Visual Studio, CodeBlocks, or GCC in the terminal, you know it spits out an executable file you can run. But under the hood, it's like an entire assembly line, transforming your human-readable code into pure machine instructions that your CPU can execute in nanoseconds. In this video, we'll visualize the entire journey step by step, from your CPP source code to the final executable. We'll cover the preprocessor, the compiler, the assembler, and the linker, with clear explanations. By the end, you'll not only understand compilation but also why errors happen and how to fix them. Before we jump into the details, let's zoom out and understand why we need to compile code in the first place. Computers don't speak C++, they speak machine code, which is basically a series of zeros and ones that the CPU can directly understand and execute. Your C++ code is high level. It's readable by humans, with things like variables, loops, and functions. But to run it, we need to translate it into low-level machine instructions tailored to your computer's architecture, like x86 for most PCs or ARM for mobiles. This translation isn't a one-step magic trick. It's a multi-stage process, often handled by tools like GCC, GNU Compiler Collection, or CLang. For our example, let's use a simple Hello World C++ program. Imagine this in a file called hello.cpp. When you compile this with command, a whole chain reaction starts. Let's follow the journey. Preprocessing. This is like the editor of your code. It handles all those hash directives you see at the top of files. The preprocessor scans your CPP file and does a few important things. Header inclusion. That hashtag include IOStream tells it to copy-paste the contents of IOStream header file right into your code. Headers contain declarations for things like std:\cout, so your code knows what they are. Macro expansion. If you have used macros like this, it replaces every pi in your code with the value of pi. Macros are like find and replace on steroids. Conditional compilation. Stuff like this lets you include or exclude code based on conditions, great for debugging. Comments removal. It strips out all comments, as they're just for humans. The output? A temporary file, often with a I extension. This is your code fully expanded, without any high-level abstractions hidden. Why is this important? Without preprocessing, your code would be bloated with repeated declarations, and macros wouldn't work. But watch out, macros can lead to weird bugs if not used carefully, like unintended expansions. In our hello.cpp example, after preprocessing, the file balloons because IOStream is huge. It includes definitions for input-output streams. But don't worry, it's all text at this stage, no translation yet. To visualize, let's just run only preprocessing stage with the following command. See how it's grown? That's preprocessing in action. Next up, the real compilation. Now we're at the heart of it, compilation. This stage takes the preprocessed I file and translates it into assembly language, a low-level, human-readable version of machine code. The compiler is like a translator. It parses your C++ syntax, checks for errors, like missing semicolons or type mismatches, and generates assembly instructions. Key steps inside the compiler. Lexical analysis. Breaks code into tokens, keywords, variables, operators. Syntax analysis. Builds a parse tree to ensure grammar is correct. Semantic analysis. Checks meanings, like is this variable declared? Or does this function return the right type? Optimization. Smart compilers like GCC optimize for speed or size, inlining functions, removing dead code. Code generation. Outputs assembly code, specific to your target architecture. The result? An assembly file, often with S extension. You can run the following command to convert I file to S file. Assembly looks cryptic. It's the bridge from human code to machine speak. Assembly. This is a quick but crucial step. The assembler takes the hello.s file and converts those assembly mnemonics into actual binary machine code, zeros and ones. It's straightforward. Each assembly instruction maps directly to a binary opcode. No more analysis, just translation. The output? An object file, with extension O or OBJ. This contains machine code, but it's not executable yet. It's like a puzzle piece with symbols that need resolving. In our example, Hello.o would have binary for main, but references to std, cout are still placeholders, pointing to external libraries. This stage is fast, but if your assembly has errors, you'd catch them here. You can run the following command to generate object file. You can disassemble object files with tools like objdump to see the hex codes. Last but not least, linking. This is where the magic happens, or breaks. The linker takes your O or obj file and any libraries and resolves all those undefined symbols, and combines them into one executable file. There are two types of linking: static linking and dynamic linking. Static linking copies library code into your executable. This makes file bigger, but self-contained. Dynamic linking links to shared libraries at runtime. The executable is small, but needs libraries installed to run. In our hello.out, the linker finds the actual address of std, cout in the standard library and patches it in. It also handles multiple files. If you have math.cpp and main.cpp, it links their object files together. There you have it, the full journey from CPP to executable. We visualized preprocessing, compilation, assembly, and linking. Understanding this makes you a better programmer,